In this lesson, we're going to be looking at finding the volumes of figures that can be defined in an xy plane, except they're three-dimensional figures. We want to find their volume by using cross-section. Basically what we're doing is taking cross-sections and finding the area of each one, adding all of those areas together to find the volume. Okay, I'm going to try to give you a physical example of what's happening here. Notice here we have a parabola turned on its side, the x equals y equals squared, and we have a region that is being cut off here. We could think about having the area there, and if I was going to fill that, we would already know how to find the area between those curves, but let's say that we're putting a solid inside of that region. Notice that the boundaries of the solid are defined by the curve, but what's important here is noticing all of these cross sections that are forming this. Each one of these is, well, supposed to be an equilateral triangle that's coming together and forming cross sections to create a solid through that. So here at the end, where we're close to the beginning and we have a very narrow piece, all those are very small triangles. Whereas as we move further down, each one of those equilateral triangles gets a little bit bigger because the base of each equilateral triangle is defined by the width of that region in that section. Okay? Now, looking at these, I would be going one way. Notice the way that this thing is sliced. All of these things are essentially slicing the y-axis. And so we would use dy with this one because of the direction that that's going. Okay, turning the graph in the other direction is going to change the way that our solid is going. Mostly what's important here is noting the change in the direction of our slices. All of them are now vertical. And so the width of each one, so we want to think about the width of each one. What is it slicing? That width of each one is now an x value. As opposed to before when it was turned this way, the width of each interval was a y value. So since they're going this way, it's slicing the x-axis, so we're going to use dx to find this one. Now also notice the curve defines one edge of this figure and a line defines the top. So a region like this does need to be enclosed between two curves or a curve and a line. So if we examine these cross sections a little more closely, notice that as I pull these off, each one is a circle. Using the same concept, I could also take other figures as my cross sections. For example, here I've got circles. Now the circle of this, each one of them, it has the center as being the axis. So notice what's really defining the area of each of these deals with the radius that's being formed here. Okay, so each one of these cross sections has a radius that's defined by the length of x in our curve. If we look at the direction of our slices here, each one has a width or a height that is a dy value because of the direction that it's going. If we flip this thing again, going back to the one that's going this direction, you'll notice that this is now slicing the x-axis. The width of each disk is now dx instead of dy. Using the integral, we can take really small slices and add all of them together going from A to B in order to get area. But in this one, if we're looking for volume, if we add the areas of each of those cross sections, we'll be able to find volume. So the key to these is finding the cross section of the area in terms of x and taking an integral that's going to give us a volume. So these are the four steps that we're going to follow, but this is really the key step that we need to look at today. It's what it means to find the area of that cross-section, and then the rest of the steps will come together for us. In this first example, they've given us certain parameters about a square-based pyramid. Now they tell us, first of all, that the pyramid is 3 meters high, so we've got a height of 3 meters running through this, but that could also be represented on this two-dimensional plane here if we think of this as x and y, so that we have an x value that's running from 0 to 3. We also have a height that is, or a base that's 3 meters on each side, and so looking at that in a two-dimensional plane, it could mean that we're running from 1.5 down to negative 1.5 in order to give us a height of 3 there. So I draw this, it's maybe better to draw these as a two-dimensional cross-section in the XY plane, because that's going to help us see where these cross-sections, how to find the area of each cross-section. Notice that each one of these squares would basically be coming down something like this, with that cross-section running through there. As we get closer to the top, these things are going to get really small. At the base, we've got a big square, as we do over in this picture here. And so we want to find the equation that would go to this. Okay, so drawing again, we're thinking about that 1.5 there. This side has an x value of 3. So if we think about this line right here, notice that we could rewrite that as the line y equals 1/2 x. Now, what we want to really find is the formula for the cross-section, which each cross-section was told that they are all squares. And so we need to think about how that compares to this picture over here. If I look at this little red line that's running through here, then I can see that that's going right to the center of my square. Now, my x value would be down here, which means that the height of this is actually my y value. But I need this height to be in terms of x, and so I can write that. We just found y is equal to 1/2 x. Since that cross-section is going to be running through the center of my square, that means that the side of the square is going to be x, which means all sides of the square are x, meaning that we have a formula for area in terms of x, which is x times x, or x squared. So we've just found the area of the cross-section, and so we can put that into an integral in order to solve it. The integral then is going to have the area inside of there. We're slicing with respect to x, and then we need to find the limits of integration. Well, we look at what our x's are doing. We started at 0 and we keep going until we get to 3. So our limits of integration are 0 to 3. This is going to give us the volume. We can work that out then. Working this out, take our antiderivative from 0 to 3, which is going to give us 1/3 of 27 minus 0, which is equal to 9. Now, they didn't give us units, but just remember that this is volume, so if they had given us units, it would be units cubed. Now, the key to this lesson is really understanding how we can draw these cross-sections. And so if we're thinking about this region here, I've got a parabola on its side, and we want the cross-sections to be circles, then it's a good idea to draw this somewhat in perspective. Just get a few circles out on here and think about how we can find the area of each one of these as we move from left to right. Now, looking at that, we should know that the area of a circle is equal to pi r squared. And so what we really need to find is radius. The way that I've drawn these circles on here, we can see that the radius is drawn right up here. It's going from the, whatever our x value is, it's going from the y or the x-axis up to the curve x squared. So the radius of each one of these things, no matter where we are on our axis, is our x value taking the square root of that. And so if we take any one of our cross sections, the area with respect to x will be pi times the square root of x squared, or pi x. Writing that as the volume then, we don't know our limits of integration here, but whatever they are, a to b, we put our area in here in terms of x and dx, and then we could find the volume. In the next picture, we have the same curve, but this time we're asked to use squares perpendicular to the x-axis with bases on the xy plane. Okay, so the base, this green side here, needs to be perpendicular to the x-axis, which means this thing's going to be running up and down. So I've drawn these somewhat in perspective, coming up off the plane. What's important is that green line there is representing the base of this thing, which is running between the curves. I could draw smaller cross sections as well as we move from left to right, and we could maybe make these fit a little better. Now, as we're moving left to right here, then, we can try to analyze what this is doing and figure out at each point, notice that it's half the distance here, half of this base is our square root of x. So if I want the whole side of this, it's going to be 2 times the square root of x, 2 times the square root of x, giving me an area in terms of x, which would be equal to 2 square root of x squared, or 4x. Again, now we have an area of the cross-section in terms of x. We can find our volume. Whatever our limits of integration are, we're probably starting at 0 on this one. 4x dx. And after we know those limits of integration, we could go back and solve it. In this next example, we're also using squares, but if we read the directions carefully, it tells us that the diagonals are on the xy plane. So I need this green diagonal here to be running between the curves. So if I move each one of these in here to try to represent this, okay, this side's coming out, this side's going down below our plane, this one's side's coming above the plane, and so we get all of these various cross sections here. But we need to think about this in terms of the diagonal instead. So coming over here, if we think about each half of this, thinking about each half, we're going to have halfway through the diagonal is the square root of x. I need to think about what this square is doing then. If I cut this into smaller right triangles, if you remember your Pythagorean theorem, then or what's special about 45, 45, 90 triangles, this side is going to be the square root of 2 times the square root of x. Or each side of this square is going to be the square root of 2x. Our area then, again, area of a square is a side squared, and so we get 2x for the area of this. Our volume then is the integral that contains the formula for area with respect to x, and then whatever our limits of integration are. For our final example, we're using equilateral triangles perpendicular to the x-axis. Now we also have bases in the x-axis, but as we move these over there, notice that the center of each side here would be, based between these curves, it's always going to happen along the x-axis. So this green value right here would be representative of our square root of x. Okay? And then if we would draw this, it would look something like this, where these are all coming up off the plane, the base being flush on the plane. And so we're going to need to figure out this height over here. Okay, so again, looking over at this curve, this green line here is the square root of x in terms of its height, and that's represented over here by this green line. So the base of our triangle, when we want to find the area, is going to be this whole side here, which would be double of that. The height of this curve then, knowing that this is a 30, 60, 90 triangle, because it's equilateral, we can just multiply that times the square root of 3. So the square root of x times the square root of 3. The altitude of this will be the square root of 3x. That will be true for every cross section. So my area, with respect to x, this time it's a triangle, so 1/2 the base, 2 square root of x, times the height, the square root of 3x. We can simplify that. These x's will be able to come out, the 2's cancel out, leaving us with x square root of 3. Our integral then to find the volume will be whatever our limits of integration are, the area of a cross section with respect to x dx.